of objects. Now, does everybody understand that phrase, names of objects? There's no one in here who's getting a headache trying to understand that, right? No. But the book doesn't call it that. They have a fancy phrase. Individual constants. Now, if you have a headache trying to understand that, you're justified, because what does that mean? Individual constants. Huh? Why not simply say names of objects? So I'll put both down. And the reason why is people in logic call objects individuals and names are constants. But we can't go into this because we really don't need to know about constants and for this course. Okay, so what will they be? They're going to be lowercase letters of the English alphabet. So there's nothing new to learn. Oh, did everybody hand in their exam? The midterm? Everybody handed in? Good. I hope I will have it graded by next Tuesday. The reason I'm saying that is that not because it's going to be a ton of work, but I'm going to a conference and I'm not coming back till Monday, and then I have to teach a course on Monday afternoon, so that leaves just Monday night. So hopefully I'll be able to finish the stuff by Tuesday. But you know, when you go to a conference, you don't bring your work with you. You bring your scholarly stuff with you. Anyhow, those are the names for objects. Lowercase letters of the English alphabet. Okay, we also need names for properties. Verbs. You can think of them just as verbs. We need verbs and how to symbolize them. So we need names of properties. And these two have a very fancy name in the book. They are all called predicate constants. And now this is going to be very hard for you to follow because you're going to get confused. Verbs will be uppercase letters of the English alphabet. And that's where your confusion starts, because atomic sentences are also symbolized by uppercase letters. So isn't that a mistake? You can't have the same, you might be thinking, you can't have the same symbol for both atomic sentences and verbs, which are very different. A verb is part of a sentence, it's not a whole sentence. The answer is, although right now it sounds confusing and stupid to do it, you will see you will never ever get confused about whether an uppercase letter is a verb or an atomic sentence. You'll never get confused about that. You'll never be in a position where you can't figure out what it is. So that's why it's done. something you already know about from sentence logic, but in sentence logic, we only use them to talk about proofs. They were not used in proofs, and they were the sentence variables, P, Q, R. So we use them to formulate the rules of inference so they're as general as possible. But you never found P, Qs, and Rs, and so on in proofs. You always found in proofs atomic sentences and truth functions, and that was it. Well, that's where things stop. That stops right here. Because what you will find is that the variables we introduce will be used in proofs. And you'll see tonight why you got to do it that way. And these variables will not be over sentences. They will not be sentence variables. We want instead variables whose values are objects. So they are called individual variables. And they are placeholders for objects. And we're going to restrict what letters we can use for them. Restricted to X, Y, and Z. And if you need them, U, V, W. Those are the 6 letters, and only those 6 that are allowed as individual variables. Variables whose values are objects. So the value of these variables are these things. A, B, C, D, E. Those are the names of the objects, whatever they are. Okay, finally, one last thing. Quantity. Quantities. And we're only going to have 2. All and some. Those are the only 2 quantities we will use in this course. Some logics bring in more quantities than that. But in this logic, we will only use all and some. And now you're thinking right now, this is going to be so easy, because who in this class, has a problem with all and some? They're crystal clear. Does anyone go home at night and worry about what they mean? Oh, they're easy. So you're thinking this is going to be a breeze. Okay, but now, the first thing is we need symbols for these words. We're not going to write all and some in predicate logic. And so this right away brings in okay, this is the symbol that doesn't have to be an X, it can be any variable in there, for all, and that's the symbol for some. So, yeah, that looks very strange. But you're thinking, it's still going to be a breeze, because whenever I see that funny looking backwards E, I'll just think some. And whenever I see the parentheses with the variable inside, I'll think all. So no big deal. And these symbols have names. This is called a universal quantifier. And this is called an existential quantifier. That existential, don't think that's, you know, existential philosophy. And you're going to get a big dose of it if you write that symbol out. It just means existence. The symbol of existence. And the way to read that is something exists. There is something. The way to read the universal quantifier is not everything exists, but rather everything has some property. So right away, there's a funny difference between those two. The existential quantifier is making an existence claim, saying there is some object that exists with some property. The universal quantifier doesn't say everything exists with this property. It simply says everything has this property. And that's the language of predicate logic. That's nothing more than that. So those are the four things we add to sentence logic. And what this means is that all the rules of inference for sentence logic hold for predicate logic. So you're not going to have to learn really many new rules. So everything you've learned so far stays good. Everything about sentence logic stays good. Nothing has to be changed. But we will need to learn new rules for the quantities. 4 new rules for the quantities. Inference rules, and 1 rule that's like the middle 10 for sentence logic. It tells you how to rewrite quantities in logically equivalent ways. In fact, it'll tell you how to do something that to you may sound like it couldn't be done. I can rewrite a universal quantifier as an existential quantifier, and I can rewrite an existential quantifier as a universal quantifier. And that's, you may think, how can you do that? But remember, you didn't think you could write a wedge as a horseshoe until we showed you how to do it. So you'll learn 4 new rules for the quantities, inference rules. And they are very tricky. I won't lie to you. They are so tricky that the authors of this book, well, I don't have the inside cover anymore, it disappeared, but the inside cover that's got all of the, thanks. The inside cover, this probably has a mistake because this is an old copy. What's the edition? 2003. Yeah, this has the error in it. This, you have this in your PDF. The sentence logic rules and the predicate logic rules, the new ones. And 4 of them are for the quantities. And 1 of them for the universal quantifier no, this is okay. Must have been the edition before this. Anyway, they're so tricky. For years, they had to make. The authors of the book had a mistake in here, the statement of the rule. And when I first saw it, I emailed the publisher, which is worthless because they don't know. They don't have anybody there who knows the stuff. finally I had to get in touch with one of the authors of the book, not the dead one, because he was dead before I noticed that. He's been dead for 22 years. It says deceased in the cover of the PDF you have, so you can find out who it is. But I got in touch with one of the authors, and the guy said, you know, you're right. I never noticed that. It just doesn't say much. For a professional who's supposed to know this stuff backwards and forwards. So they eventually changed it. But the point I'm making is that it's very tricky. That's the point I'm making. The quantity words are really tricky, and we will have to spend a lot of time with them. The book has a very bad, most logic books have a very poor treatment of these subtleties. And what I've done is to develop ways of thinking about these subtleties that appeal to your imagination. In other words, what I want to do is to show you why we have these subtleties involving the quantity words. And so I ask you to imagine how the universe, the world, would be different if we didn't have these subtleties. And it's amazing how strange the world would be if we didn't have these subtleties for the quantity words. But none of the books do that, as you know, in teaching this material. So that's why I think I've got a better handle on teaching this stuff than the books do. Because when you vividly see what difference it would make in the world to whether you had these subtleties or not, then you can see that they're very important. But if you just present the subtleties very abstractly, as the book does, it just looks like meaningless junk. It's like learning, you know, that's the problem with technology. You know, it's like learning how to use something like a cell phone, where most of the, you know, where many times the rules are totally meaningless. Do ba 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 boop, and then leap da da over to the deet deet. You know, they have just like these words, and you eventually figure out how to do it, but they're totally meaningless. That's why I hate, you know, technology. Not the actual things are fantastic, but the guides for using this stuff are the worst ever. And then the designs, they're not so hot either. People don't think about designs. It's amazing. Even with obvious things, the designers don't think. Car windows. I had to rent a car yesterday and today because my own car, the front end was making noises, but not much. And I was going to bring it into the shop on Wednesday. And then I spoke with a friend of mine who knows a lot about cars and said, those are the kind of noises that belt problems create. And so as soon as I heard that, I said, I'm renting a car. Because you don't want to be on the Jersey Turnpike and have your fan belt break. If your fan belt breaks, you cannot drive, or you're going to ruin your engine. And you have to have somebody come and tow your car. And you're on the Jersey Turnpike in a breakdown lane. It's not uncommon for cars and trucks to crash into cars in the breakdown lane. I read about these accidents all the time. You know, you probably have heard about them yourselves. So I rented a car, a Nissan, big car, for $44 a day, which isn't bad. And what's my problem? The windows, the side windows on the driver's and the passenger side go up higher. They're making windows bigger. So, you know, maybe the windows might look like this, the old ones, but now on the new cars they go up a lot higher. And here's the problem. You're driving and the sun is making an angle into your car. When the windows aren't as high, you're not going to get the sun going into your left eye. But when the windows are higher, the sun goes right into your left eye, and it was unbelievable. I couldn't believe how irritating it is to have the sun going into your left eye, and there's no thing you can pull down on the driver's side window. If the sun is directly in front of you, you can pull down, you know. That's the problem with a window that's that high. It lets the sun hit your left eye. Bad design. Does anyone notice that problem? Nobody. All right. So, anyhow, funny language, bad how to use manuals, bad design of technology. Let me just close that with, there is somebody who actually is an expert in badly designed technology. The psychologist Donald Norman, N-O-R-M-A-N. He's been in business, well, he's been in academia for many years, and he's written several books, and he's probably the world's leading expert on design of technology. So if you see any of his books, they're worth, many of them are in paperback and are not technical books. They're worth reading. Very interesting thinker. He's a psychologist, Donald Norman. Okay, I had to put that in because, you know, right off the bat, as soon as I'm talking about this car, you're thinking, well, that's you, Professor. What do you, that's just, you know, your idiosyncrasies have nothing to do with design. Maybe you're thinking that. Still, it makes sense. You know, the higher the window on the passenger's and the driver's side, more opportunity for the sun to come in. And if there's nothing you can do if it's hitting your eye, your left eye. It was really irritating my left eye. But my own car doesn't have those high windows. It's 10 years old. And they, you know, I guess this is a recent change. So I started noticing cars, you know, after you do this, you start thinking about, you notice cars in the side windows. All right, this has nothing to do with logic anymore, so we should get back to. Okay, so here's our argument. And let's proceed to translate it into predicate logic. Is Jerry an object? Yes. Is smart a property? A verb? Yes. Is Rutgers Newark student a property? Yes. All Rutgers Newark students, are they objects? Yes. Okay, so we need, since that's an object, we need a name. So let's just use little j. And smart, we need a name. Let's use big S. Now here's the convention in logic. Almost every language on earth is a subject, verb, object language. There are some languages that are verb subject. Does anyone here, is their first language, anyone in this room whose first language is a verb subject object language? There are not a lot of them. Okay, what we're going to do is not do subject-verb in predicate logic. We're not going to write that as this. That is not the way you say Jerry is smart. We're going to make it verb-subject. In other words, this is predicate logic translation of Jerry is smart. Big S, little j. So you just have to get used to that. Jerry is a Rutgers Newark student. Let's let that property be R. So that's RJ. I don't know why that's the convention, but that's the way it is. Okay, now comes the hard part. If we didn't have these quantity words, the only way to say that all Rutgers Newark students are smart would be to write down 40,000 of these for each student. In other words, if we didn't have the quantity words, we have to say RJ and SJ, RA and SA, RB and SB. Okay, we'd have to write all those out. But we have the quantity words. In other words, we have variables. Remember the problem for writing out whiffs in sentence logic. If we didn't have sentence variables, we'd have to write every whiff out using the squiggle to say which ones are whiffs and which ones are not. With variables, all we had to do was say, that's a whiff. Same thing here. All we have to do is talk about a set of objects, all the objects. Now, we're not going to say all the objects and restrict them to students. We want logic to be as general as possible. So when we say all objects, we mean all the objects there are in the universe, every one of them, including the non-physical universe, numbers, abstract things. So when you see that, that means every object. And now what we have to do, the price you pay for this generality is that you can no longer, after it, say, Rutgers student and smart. You can't have A and B. Rather, you have to do something to select from all those objects just the ones that are Rutgers students. Sounds technical, but it's really simple. Not as simple as walking around this room. Here's how you do it. Look at all the objects in the universe. If one of those objects is a Rutgers student, then that object is smart. So this thing to the right is a property that the objects have. And each object in the universe, that property is true of it. If it's a Rutgers student, then it's smart. So what this does, this thing, it's called the matrix. And that's the quantifier. This is the property that the objects specified by this quantifier have. Every object in the universe has this property. This pen has the property that if it is a Rutgers student, then it's smart. It's not a Rutgers student, so the horseshoe is true of it. Because remember, a horseshoe is true if the left-hand side is false. And that's the trick. That allows us to specify the subset of objects in the universe that are both Rutgers students and smart. But you don't do it this way. That's not going to select a subset. That says of every object in the universe, they're Rutgers students and smart. So this would be this, if true, would mean this is a Rutgers student. Did it pay its tuition?
It's smart.
The registrar would like more students to pay tuition. This would be a Rutgers student. This would be a Rutgers student. They'd all have to pay tuition. Yes?
Okay, so you just said actually reminds me of the triviality thesis. It's like, it's making a claim that every object in the universe has every property that there is. Isn't that like too metaphysically grand there?
Oh, yeah, well, you're getting ahead of, we will not worry about these issues, but there are big issues about these about the quantifiers. And to say that every object has every property, no matter what it is, or doesn't, to say that every property is applicable to every object, it either is or isn't, This property, and if you put it in the form of a horseshoe, every object does have this property. That's the property of, if you're a Rutgers student, then you're smart. It's a complex property, but every object in the universe has it. And also just to say, of every property, each object either has it or doesn't have it. So it's either true or false of that object that it has it. That too, if a property isn't applicable to an object, we really don't want to say it's false that it has it. We simply want to say it doesn't apply. And there are interesting cases where that there's a distinction between saying it doesn't apply and it's false that it has it. But we're not going to worry about that in here. But yeah, you're pointing to these issues that come up. And then the other issue is how many, how much is all? What does it take to truly exhaust everything? And that too, there was a book that came out a couple of years ago called Everything, and a collection of essays where people were worrying about what counts as everything. Well, we won't have to worry about these things in this course. Only the philosophy majors. Only the philosophy majors will have to worry about this in this course. So that is how we rewrite this argument. And so the problem would be prove this. And now, let me, going on 7, right? Yeah. Let me give you 2 facts that are so important. Everything you do in this course from now on follows from these 2 facts. What are they? Fact 1. And I'm putting these up because you won't be able to see how to do this proof until you have these 2 facts. A universal quantifier say is truth functionally equivalent to an infinite conjunction so for all x, fx is equivalent to an infinite conjunction. A has f, and B has f, and C has f, and D has f, and just on for all the objects. So that's the big fact. A universal quantifier is really just a conjunction where you replace the variables by the names of the objects, each one of them in the universe. Similarly, fact 2, an existential quantifier say there exists an x, fx is truth functionally equivalent to an infinite disjunction. Fa or Fb or Fc. And this is the essential difference between universal and existential quantifiers. So an existential quantifier is truth functionally equivalent to an infinite disjunction, Fa or Fb or Fc. Why? When you say something has F, you do not know which object or objects have F. So the best you can do is to say A has it, or B has it, or C has it, and so on. However, when you say everything has F, you know every object has F. A has it, and B has it, and C has it, and so on. So right away you can see how to solve this problem. That's universally quantified, and every object has that property, including the object J. So by simplification, out of this big conjunction, I get Rj horseshoe Sj. And we'll learn that the rule has a name, but don't worry about it tonight. And then by one step, modus ponens, and we're done. So there was just really The hard part was line 3. And that's not that hard.
What does that say?
What's that?
What's in line 3? What does it say?
Yeah, that's, I'm using this rule and applying it to this line to get that line.
Yeah, but what's the abbreviation for it?
What does it mean?
Yeah, what's the abbreviation?
What does it abbreviate? Oh, I didn't want to say. It's one of the 4 inference rules for predicate logic. It's got a fancy name. Universal instantiation. I didn't want to say it, because it makes people start to quiver when they hear that fancy word. Sounds very, technical. But it really, universal instantiation just follows from fact 1. Given any universally quantified sentence, it's just a big conjunction. And I can simplify out any of the conjuncts. So really, that's all I did in line 3. I simplified out the conjunct where the object was Jack, or Jerry, whatever the guy's name is. And one step, modus ponens. Looks like a breeze. That's good news. The good news is that the sentence logic part of these proofs in predicate logic will be very easy. This is the sentence logic part of the proof. It's just one modus ponens, very easy. This is the predicate logic part of the proof. You will find the predicate logic part of the proofs harder than the sentence logic part. And the only reason why is that it will take you a couple of weeks to adjust to all those X's and Y's and Z's. They're going to look very strange. Especially when you start learning the rules in detail, the 4 inference rules. They're going to look strange. And there's no getting around that. After a while, it will no longer look strange. It's like, anyone ever hear about these experiments in psychology with vision inverting glasses? When people, I don't know how you get people to agree to go on, but they have them on for weeks, or maybe days. And initially everything is inverted, and then at some point you get used to them and you start seeing things right side up instead of upside down. Has anyone actually participated in one of these experiments? The psychology department has 2, they have they spend a lot of money on these things, but they have a car. Have you ever ridden in the car? It's a car. It's just, it doesn't move, but they have a way of making it feel to you like it's moving. And going over hills, going over rocks, crashing. Let me tell you what they can do. You can feel like you're in a car going 180 miles an hour, and you're scared stiff, because they project on a huge wall scenes of, environments. And they'll have you in this car going over rocks and hills. Well, the car will go over a hill at 80 miles an hour and then go airborne. And the very end of this tour, you go up a mountain in this car, and you know what the last thing is that they have? You go off the mountain. I myself couldn't handle that. When I went up, when that car started climbing up the mountain, and I saw what was going to happen, I said, "Stop! I'm getting out." They also have a virtual reality setup. And this is 10 years ago. I haven't been over there. This was 10 years ago where they showed me how all this stuff works. And they must have more sophisticated virtual reality software. Has anyone actually done virtual reality software? Yeah, it's unbelievable. What you think you're doing. They create environments that don't exist. You're just in a room, bare room with nothing. But it looks to you like you're in some strange environment with like threatening things, like holes in the ground that are 100 feet deep, creatures that can come out and grab you. It's scary. If they program this stuff into it, it can be very scary. So that's what your tuition money is going for, and I'm just joking. They're really psychology department is an excellent department. Really, really good people. Very, very smart. Very interesting research. But they don't talk about these, the car and the virtual reality stuff. Have you haven't been in the car, right?
Yeah.
No. See, they keep it.
I don't know which researcher works with virtual reality right now. I don't know the only person working with virtual is Carl Dr. right now. So I don't know who works with that kind of stuff.
Yeah. Well. Okay, so now that we have the two facts, we can, and these facts you really need to keep them in mind. We can progress. Oh, here it is. Let's see, I think we can do it tonight. 4 free quizzes. Let's think about something we didn't do in sentence logic, and that is translating sentences from English into sentence logic. We didn't do much of that, almost nothing. But we do need to do a little bit of that in this course. And we need to get some basic ideas about how this works. So, this is a very basic sentence. Everything has F. Okay, how would we say nothing has F? We do it like here's 2 possibilities. Okay, one of these says nothing has F. Is it number 1 or number 2? One of them says nothing has F. Which is the one that does it? Who says number 1? Who says number 2? Okay. The correct answer is number 2. Most of you intuitively thought it would be this. It's not the case everything has F, but that doesn't say nothing has F. This number 1 simply says not everything has F and leaves it open that there are some things that do have it. But this one makes it clear. Every object does not have F. Nothing has F. So they say very different things. Nothing. So now we want to this says something has not F. And this says there is nothing that has F. There is no object that has F. Or another way of putting it is there is no object Okay, so they are very basic sentences. We won't do it tonight. Yes?
Something has not, is that a squiggle F?
Which one?
Number 5, not like squiggle?
Yeah, that's squiggle. So that's exists in X, squiggle, fx. So when I draw straight lines, they're squiggles. All of these straight lines are squiggles.
And like, so something has not F?
No. Number 5 says something has the property not F.
But you wrote not and a squiggle.
What's that?
You wrote not and a squiggle, so you
Shouldn't be a
double
squiggle.
negated yourself.
In number 5?
Yeah,
Yeah, and then sentence.
No, there is some object
In the written
that
thing.
does not have F.
No, in the justification.
Which no one?
The
In the
justification.
so to the right.
Something has not.
The justification.
Something has
In the sentence.
not.
In the
In the
sentence.
sentence.
Like this thing?
No, to the right of it. The right. The
On
right.
the right side.
I don't see. Oh! That one. Yeah, I just wanted, you see, this is not in logic. So when you're not doing in logic, the hyphen doesn't mean squiggle. It just means not, that means not F. When see, that's English. That's the convention. Okay, I understand now what, yeah. Yeah, it's a hyphen, not a squiggle. There. So, thank you, but that's important. So that's worth a bonus. Because that's an important, many students in the room may have seen that as a squiggle. But it's a hyphen. That's a squiggle, not a hyphen. That's a hyphen, not a squiggle. We will look at, not tonight, how to say complicated things about objects. But what I want to look at tonight, and this will give each 4 people a chance for a free quiz, is, and this is not in the book, but it's very important to know, the way in which universal and existential quantifiers interact with the truth functions and or. So there's 4 things to look at. Okay, so the first one, and let these properties be sweet and bitter. So sentence number 1 says, everything is sweet and everything is bitter. Sentence 2 says, everything is sweet and bitter. And there are relations, inference relations between sentence 1 and sentence 2. One possibility is 1 implies 2 and 2 implies 1. So one possibility is that when 1 is true, 2 is true. And when 2 is true, 1 is true. Another possibility is that 2 does not follow from 1, but 1 follows from 2. Another possibility is 2 does follow from 1, but 1 does not follow from 2. And the fourth possibility is 1 doesn't follow from 2, and 2 doesn't follow from 1. One of these 4 possibilities is the truth about the inferential relations between 1 and 2. Here's how you can win a free quiz. I'll only take 4 names, 1 for each one of these. If you think any one of these is the truth, put your initial in this box. Anyone can just run up and put their initials. Go ahead.
What? What is the question?
Which one is correct?
Put your initials.
Just one initial in one of those. Yeah. Well, anybody can come up. No, just one. Oh, the whole name, your both initials, but just once. In other words, that's now taken. There's 3 other possibilities. You can win a free quiz. If you're wrong, you're wrong. You don't win. That's all. Still one left. There are going to be 16 opportunities. We're going to have 8 sentences total, and each pair of sentences will have 4 possibilities. So one of these is the truth. One person will win the free quiz. So let's see what the truth is. Okay, the first thing we'll look at is whether this is true, whether 2 does not follow from 1. So let's think about it. If everything is sweet and everything is bitter, does it follow that everything is sweet and bitter? By conjunction, it's true. Every object is a sweet object, and every object is a bitter object. So every object is a sweet and bitter object. Conjunction. That rules out this and this, and leaves open these 2. Okay. Now, let's look at whether 1 follows from 2. When 2 is true, is 1 true? If everything is sweet and bitter, is everything sweet? Simplification. And if everything is sweet and bitter, is everything bitter? Simplification. So 1 follows from 2, and this is the winning. Who won this? Okay. Now, here is the way things work. If you win, you are no longer eligible for future quizzes tonight. If you didn't win, you are eligible to go to the board again. Now you can see, if you know the answer, when I write those two, you rush up to the board. Initially, you didn't know. Here are the next pair of sentences. This says everything is sweet or everything is bitter. This says everything is sweet or bitter. And here too, there are which one? Okay, I want to get it consistent with.
Can we both close and answer?
You can't, only the open ones.
It's the first.
Oh, well.
Okay. So, let's see whether this is true, whether 4 does not follow from 3. So, when everything is sweet or everything is bitter, does it follow everything is sweet or bitter? Addition. If everything is sweet, then everything's sweet or bitter. If everything's bitter, then everything is sweet or bitter. So 4 follows from 3 by addition. Ruling this out, does 3 follow from 4? If everything, each thing is sweet or bitter, is each thing sweet? No. If each thing is sweet or bitter, is each thing bitter? No. So 3 does not follow from 4. And so, okay, so that's the second winner. So we have 2 winners and 2 more. Oops, I should have done it the other way. Okay, 4 4 possibilities. Two left. One left. One left. Okay. So let's just think about what these say. This says something is sweet. There exists something that's sweet, or there exists something that's bitter. And this says there exists something that's sweet or bitter. Now, many of you did not want to put your initials here because you looked at this and that had a problem. And so many people are thinking that if this one had the problem for universal, then that one's going to have the problem for existential. So let's see if that's true. So let's look first at whether when 6 is true, when 5 is true, 6 is true. Does 6 follow from 5? If there is something that's sweet, or there is something that's bitter, is there something that is sweet or bitter? If there's something that's sweet, then surely there's something that's sweet or bitter. Or the other possibility, if there's something that's bitter, there's surely something that's sweet or bitter. So 6 follows from 5, ruling out those two. Now, does 5 follow from 6? If there's something that's sweet or bitter, is there something that's sweet? Now here you can't do it by cases, because this would be invalid reasoning. There's something that's sweet or bitter, therefore there's something that's sweet. That doesn't follow. Right? There's something that's sweet or bitter, therefore there's something bitter. That doesn't follow. You can't reason that way. However, this is how you reason. If there's something that's sweet or bitter, then there's either something that's sweet or something that's bitter. And so, 5 follows from 6, ruling out that, and that's the winner. They are logically equivalent. One and 2 are logically equivalent, and 5 and 6 are logically equivalent. That's the one that gets crossed out.
This time I actually thought about it.
Okay. So let's just read these. there is something that's sweet and there is something that's bitter. And this is, there is something that's sweet and bitter. So when 8 is true, is 7 true? If there is something that's sweet and bitter, is there something that's sweet? Yes. And if there's something that's sweet and bitter, is there something that's bitter? Yes. By simplification. And so 7 follows from 8, ruling out
Wait,
these
Professor,
two.
Professor, you crossed out one that follows and one that does not follow. Professor, like you had 7 follows from 8 and then you crossed it out with the initials
Oh.
B. Yeah.
Wait, that 7 does not follow, sorry, 7 does follow from 8.
Yeah, so that one is
So
correct.
that's wrong, and that's wrong too, because that says 7 doesn't follow from 8.
Oh, we're looking at the, okay.
Remember, the last one,
Oh.
neither follows
I
from
get
the
it
other.
now, okay.
Okay. Now, let's see whether 8 follows from 7. If something is sweet, if there's something that's sweet, and there's something that's bitter, is it true by conjunction there's something that's sweet and bitter? Who says yes? Who says no? Okay. The answer is that it is no. Who wins the, okay. This is one of the most important things you can learn in predicate logic. Let's think of these S and B's differently than sweet and bitter. Because some people didn't see it. Some people thought maybe, in fact, 8 does follow from 7. Let's change the property. Snake. Bat. Do there exist snakes? Is that true? Do there exist bats? If this logically followed from 7, once there were snakes and once there were bats, by logic there must be in the world snake bats. Fusions of snakes and bats. Are there such things? Have you seen snake bats flying around? Now, some of you might say, well, maybe there are such things. So let's restrict S to be a very dangerous snake that, thank goodness, you can't find in New Jersey. It's one of the most feared animals in Africa, and that's the mamba. They are big, aggressive, super venomous, and super fast. They can move over the tops of grasses. They will strike without provocation from a tree. And if you see one in a tree, it's too late for you to run away, because you can't move as quickly as they can strike. They are one of the most feared animals in Africa. They're very, very dangerous. Okay. Do you know, so there exists mambas. There exists bats. Do you know of mamba bats? No. You would have heard of mamba bats. But if 8 logically followed from 7, by logic, there must be mamba bats. Thank goodness it doesn't. In fact, if 8 logically followed from 7, once any 2 things came into existence, their fusion would also come into existence. This pen exists. This head exists. There would be, besides this pen and me, a third object in a world in which 8 logically follow from 7, and that third object would be my head fused with this pen. It would exist independently of the pen and independently of me. For any two objects, the fusion of the two would exist. How many objects are there in this room? Each one of us is an object, each physical thing. So for each person in this room, there will be the fusion of that person with another person. And once the fusion exists, it will fuse with the other objects. So there will be, let's just take an example, you and me. I'm picking on myself, and forgive me for picking on you. If 8 followed validly from 7, then there would be in this world, in addition to you and in addition to me, the fusion of you and me. And in addition to the fusion of you and me, there would be a new fusion consisting of the fusion of you with the fusion of you and me. And the fusion of me with the fusion of you, and for every person in the room, and for every object. Overnight, the amount of matter in the universe would blow up. You would have to violate thermodynamics. You would have to create energy because matter is equivalent to energy by E equals mc squared. And so, you would violate the fundamental law of physics, which is the conservation of energy. But logic is stronger than physics. Logic dictates what physics can be. The necessity of physics, the laws of physics, is weaker than the necessity of the laws of logic, which are stronger. So if that were a law of logic, the physics of our world would be radically different, and the law of conservation would no longer hold. Thank goodness we don't live in that world. Would you want to live in that world? Where there would be, it would just go on and on. There'd be infinitely many duplicates of yourself with you and other objects. We're just considering the people in this room. How many people on the planet? 5 billion? What's the population of Earth? Is it 5 billion? 10? 7. 7 billion. Each of us in this room will be fused with each of those other 7 billion minus 30. Or 35 people in the room. Thank goodness. Thank goodness 8 does not logically follow from 7. And this is so important, there's going to be a rule that restricts you from inferring 8 when you have 7. There's going to be a restriction on a rule for using the existential quantifier. And that's why you have that restriction.
If 8 doesn't follow from 7, then Vn is the winner, right?
What's that?
Shouldn't be Vn the winner instead of mm?
No. MM wins because this is true. 8 does not follow from 7. BA said 8 does follow from 7. Okay? So. Okay, that's good. Yeah.